Okay, welcome back. Second last lecture. So before we start, today we're going to cover three-dimensional problems of the hydrogen atom, which is the highlight of the course. Next week we're going to have another tutorial in which I'll try to sum up some of the points, maybe talk a little bit more about the hydrogen atom, but also stress some of the stuff we've learned so far to make sure that everything is rounded up, put it all in a box, and be ready for the test. Today's homework is the last homework assignment. You have until I give you another extra few days, so you can hand it in on Sunday, the first Sunday of the vacations, not on Thursday. I'll give you the weekend as well, because next week there'll be no homework, but it's already the end of the semester. So one last time, and then for the test, of course, but one last time for homework. So that's that. Another thing that we'll have to do before the test is we have to start thinking about an equation sheet. So Eli has a sheet online on his webpage, which is in Hebrew, which he has been using for the past 20 years or so. In my opinion, this equation sheet is not very good. First of all, it has mistakes in it. Secondly, it uses somewhat different conventions than we used in class. So different polynomials are defined differently than we did in class. It's not wrong, but it could confuse you, especially in a test. Suddenly you see something you're not used to. So it's following different conventions. It's not that applicable. And thirdly, the equation sheet, I don't know if you've seen it, it's very long. It includes both this course and the next quantum mechanics course, and it therefore has a lot of information that is irrelevant. So in my opinion, it's a really bad equation sheet. It's really hard to use. So I recommend we make something new. I started typing something up. So if maybe some of you guys want to get together, make a delegation, 2-3 students that would sit together with me, maybe we can find something together that will make sense, that will be short enough, but good enough that you have everything you need, but you don't get confused with too much information. So maybe think about that during this week, and we can talk about this more next week. Okay? Great. Okay, so for today, we're going to cover 3D problems. Last week we did angular momentum, which was a two-dimensional problem, because we went to radial coordinates. We had only theta and phi, so we broke it down to a two-dimensional problem. For instance, we solved the rigid rotor, which could move in theta and phi, so it was a two-dimensional problem. Today we're going to also include the radial direction. So it's going to be a 3D problem. They're all going to be central symmetric, so central potentials, but there's still a radial equation we have to solve. I'm going to present the equation. We're going to solve it for a couple of examples. And then we're going to move on to the main problem of 3D quantum mechanics, which is the hydrogen atom. It's basically the most complex system that can be solved exactly in quantum mechanics. So after this, we're done with this course. So we've seen all the exactly soluble problems in quantum mechanics. The next course will be approximations. So when you get there, this is where exact physics ends. Everything after this is approximations. The approximations can be good, but they're going to be approximations. So we're going to talk about the hydrogen atom, solve a few examples, and then see something called the Zeeman Effect, which is also going to be an example. Questions before we start? All right, let's go. 3D Hamiltonian. So three-dimensional Hamiltonian consists of three-dimensional operators, and I just want to remind you that a three-dimensional operator, so a vector operator, is just a vector of operators. So for instance, the R position operator is just the X operator in the I direction, plus the Y operator in the J direction, Z operator, K direction. Just reminding you of this is old stuff. Or for instance, the momentum operator in the same way. It's actually a sum of 3 operators, each in its direction. And this is what we need to build a three-dimensional Hamiltonian, which obviously is just p squared, but now it's this p vector squared. So it's px squared plus py squared plus bz squared is actually 3 operators over 2m plus the potential, which in general depends on all 3 coordinates, so all 3 operators x, y, and z. Now we're going to limit ourselves to central potentials. Central potential means that the potential is not a function of all 3 coordinates, x, y, and z, or r, theta, and phi, but it depends only on the radial coordinate r, so only on the distance from the origin. The good thing about central potentials is we get something very important for free. In all of these problems, energy is conserved. We know that already. But in addition, for central potentials, also angular momentum is conserved. We get that for free. That's true in classical mechanics. It's true in quantum mechanics. As soon as you have a potential that depends only on the radial coordinate r, angular momentum is conserved. And because of that, the Hamiltonian operator, right, if it's conserved, then obviously in quantum mechanics, the Hamiltonian must commute with the angular momentum, because it's conserved, right? That's the Heisenberg picture. So we can write the Hamiltonian as just the momentum in the r direction, in the radial direction, plus the angular momentum term, plus the potential. Potential now depends only on r, not r vector, so there's no vector sign. And we have basically taken out the theta and the phi dependent into here. We solved this part already, so we know exactly what to do with this part. This is the only new thing for today. You can, if you don't believe that this is true, you also see this directly from here. Obviously, angular momentum commutes with itself. So the only question is, does angular momentum, the L squared, does it commute with this P? So yes, obviously it does, because this is a derivative over R, and the L, as we saw last week, depends only on theta and phi. So it's obvious that these commute. So yeah, we know if we get it for free. Also, this depends only on R. This depends on theta and phi. They're different variables. So obviously, the Hamiltonian commutes with L squared. The task is then, as always, to solve the Schrödinger equation. And the wave function can depend in general on 3 coordinates. Of course, we'll work once again on a spherical basis because of the symmetry. So we will be interested for any potential to solve the Schrödinger equation. Now, because of this commutation relation, in addition also we can choose one angular momentum projection, which will be Lz, which also commutes with the Hamiltonian and with L squared. For this reason, we can separate variables we know that the angular dependent are just the YLMs, and then everything that is not radial, everything that is not angular, so everything that is radial, which is put in this function capital R. I'll already tell you that it depends on 2 quantum numbers. We'll see in a second how that happens. And then the only unknown thing is this function here. And so we've reduced the problem to 1 dimension. Because the YLMs we solved before already. Now you did this in class, I hope you did this in class. You take this wave function, you take this Hamiltonian, you plug it in, and then you separate variables, right? And then in the r direction, you obtain an equation which includes only r. What you get the following equation. Now working in position space, of course, so I'm dropping the operator signs because R is just multiplication by R. And this sign here is the Laplacian operator in spherical coordinates with only R component. It's 1 over R squared ddr times R squared ddr. Look this up in a list, in a table. So it's obvious where this comes from. This is just the momentum operator in the R direction. And this h for L plus 1 comes from the L squared operator. That's its eigenvalue. So it's obvious where this comes from. The next step is to substitute a different function. Let's just say that, let's just take this R of R and say it is some function U of R divided by R. So now U of R is the unknown function. Of course, this is a legal step. It's just taking out the 1 over R dependence. It's a neat trick because when you do this, the Schrödinger equation reduces to a very simple form. Basically what happens is that this Laplacian operator just becomes a regular second derivative over R. That's the main point. And then the rest just remains as it was. And we can then call this part in equivalence to classical mechanics. It's a regular step that is done quite often. And if we call this an effective potential, and then, big surprise, the radial, sorry, this is U. Then the radial Schrödinger equation just looks exactly like the one-dimensional Schrödinger equation. Right, it takes exactly the same form as the regular one-dimensional Schrödinger equation, with a few slight differences. The first difference is that there's a V effective instead of a V, which means that there also is some extra term. You see that this extra term depends on the quantum number L. And since this V effective depends on the quantum number L, obviously this U and eventually the R will depend on the quantum number L. That's already given. And then you know that when you solve the one-dimensional Schrödinger equation, then you get another quantum number by imposing boundary conditions on this equation. So you get a second quantum number. And that's why I said that this R depends on two quantum numbers, N and L. L is the same L that we already had, and N is the new quantum number that you get from this equation directly. The second difference is in the boundary conditions. R is the radial coordinate, so it goes only between R and infinity, not between minus infinity and plus infinity, but it only goes from 0 to infinity. And 0 is a somewhat special point in spherical coordinates because you can go through 0. When you go through 0, then you go from let's say plus 1 to 0 and back to plus 1. What changes is the angle, right? The theta, the phi. But R just goes from positive to 0 and then back to positive. So it's a special coordinate, and for this reason you need to be very careful with that point R equals 0. So pay attention to that big difference. And one last thing, and I'm going to stress this point as we solve questions again. Remember that U of R is not the physical wave function. The physical wave function is this thing, the capital R. So boundary conditions, physical boundary conditions, must be imposed on this function. This cannot diverge, for instance. This must be continuous. these conditions do not apply for u, not necessarily. They only apply for the physical function. This u is just a mathematical construction that makes this equation look nicer and easier to solve. But when you impose boundary conditions, make sure you impose them on the physical function, not on the mathematical construction. Okay? Questions? Okay, let's put this to you. Let's solve an example. So I'll solve the simplest example you could think of now, and then in your homework you'll solve also simple questions, but a little bit more difficult. And obviously the simplest example is an infinite potential well. Your homework you'll solve the finite potential well. And in your homework, I think you also have the free particle, which is also nice. So we're going to solve the infinite potential well. But it's now a 3D well. It's a spherical well. Potential is given like this. It is 0 inside some radius and infinite outside that radius. I call it radius A. I can't really draw this because it's three-dimensional, but imagine there's a ball, right? There's a sphere. Inside that ball, the particle can live. There's no potential. Outside the ball, potential is infinite. So it's a particle confined to a sphere, to the inside of a sphere. Okay? What we would like to do, we would like to find the eigenstates and eigenenergies, so solve the Schrödinger equation. So for arbitrary L, we'll just find the equation. From which we could technically find the eigenfunctions and the eigenenergies, but we're only going to solve it for L equals 0. You'll see in a minute why we're not going to solve it for general L, for arbitrary L. It can be done in theory. I'll show you where it gets problematic. Okay, question clear? All right, let's solve it. So we already know that the wave function consists of two parts, r times y, if we're inside the well, and it's obviously 0 outside the well, because the potential is infinite. So that's where we start. And now we can set up the radial Schrödinger equation. So we know the YLMs, we do not know these r's. How do we find the r's? So we'll solve the radial Schrödinger equation, we'll find u, and then we'll take this u and divide by r, and we get capital R. That's how simple it is. So the radial Schrödinger equation for this problem, just looking up here, minus h bar squared over 2m no dou r squared, plus v effective. Now v effective has this first term, which is the angular momentum. And then there's another term, which is the potential. I only have to solve inside, and inside the potential is 0, so this is it. So this is the equation I have to solve. We can put this in a little bit in easier form. But before we do this, so from this equation, from here, find u of r. Then we find the physical function by dividing by r, and then impose boundary conditions. What are the boundary conditions? So, first of all, at r equals 0, this function must be finite. Error in spacing must be. But you see why r equals 0 might be problematic. Because this function is, right, the physical function is some u of r divided by r. So division by r could be problematic at r equals 0. So this is a point I'll have to investigate and make sure that this function doesn't diverge there. Second boundary condition, specifically for this problem, is of course the continuity at A. So at the border of the sphere, it must be 0. So this is our plan. Let's define, as usual, our k squared. Right, so let's define. You see that this function, it has h bar squared over 2m on both ends, right? In both terms in the beginning. There's an h bar squared over 2m here. There's an h bar squared over 2m here. Question? So I'm going to multiply by 2m over h bar squared and then define 2me over h bar squared as k squared. That's what we usually do. Note k squared equals 2me over h bar squared. And I also multiply by r squared. What we then get is r squared u double prime plus k squared r squared minus ll plus 1 times u equals 0. So I've moved this e to this side. Actually, I've moved this to this side so that the minus sign will be on this term. I've multiplied by r squared and I've multiplied by this constant. And this is the equation we get. It's a second order differential equation. Can be solved. Some other solution. Correct. The actual way to solve it would be to plug in a Taylor series, and then you expand the Taylor series, you get a recursion relation, so on and so forth. What you would find is that the solution are what's called spherical Bessel functions. Well, that's why in the question I say to find an equation for L, for an arbitrary L, which is this. This is the equation. I'm telling you that the solution is called a spherical Bessel function, and you can Google it later on, but I'm not going to show you how to get there, although you should know how to do this by yourself. I'm also not going to show you how they look like. You can Google that. What we're going to be concerned about is what happens for L equals 0. So we'll solve this equation just for the special case when there's no angular momentum. L equals 0 means there's no angular momentum. So notice that for L equals 0, you can reduce this equation. U double prime. So this thing falls out in total. I can divide by r squared. So I get plus k squared u equals 0. So that's a simple equation. I can solve that one, right? It looks exactly like the one-dimensional case. This happens very often that for L equals 0, for no angular momentum, your equation for u, not for r, your equation for u will look exactly like the one-dimensional equation. You'll notice that also in your homework when you solve the free particle. You'll notice that this happens. That's the reason that we did the whole substitution. So we can solve this equation. It's sine and cosine. So u of r is a sine kr plus b cosine kr, which means that the physical function, capital R, is a times sine kr over r plus b cosine kr over r. Okay, this is a very important step. Do not make the mistake of imposing boundary conditions on u. Boundary conditions must be imposed on the physical function because the boundary conditions are physical. You could, of course, translate your boundary conditions for you into boundary conditions on you. You could do that as well. I'm thinking, though, it's easier and more intuitive to write out the actual physical function, and then it's easier to think about the boundary conditions. Then they make sense. So, first boundary condition. Notice that there's an r down below, so if I plug in r equals 0, things will start diverging. So cosine of 0 is 1, divided by 0 diverges. So I must set b equals to 0. Automatically. In this case, though, sine of 0 is 0, r of 0 is 0. So this 0 divided by 0 has to be, you have to take the limit properly. So maybe you know this function as a sinc function, and the value at 0 is actually 1. So if you take the limit properly, means if you use L'Hopital, you'll find that this is finite at r equals 0, so that term is fine. So we can keep that term, and we are left with a sine kr over r. Is that clear? This is physics. It's not just stupid mathematics, this is physics. That's the stuff we like. Next step, let's use the second boundary condition. The second boundary condition will quantize k.
In the beginning, it's r between minus a and smaller than a.
Excuse me? Here? No, so I said r by definition only goes from 0 to infinity. The question was if r is, if I mean here between minus a and plus a. So no, that's what I said in the beginning. R by definition is the radial coordinate. It's in the range of 0 to infinity. Right, so if you go through the origin, right, I mentioned that you go from 1 to 0 and then back to 1, not to minus 1. Because it cannot take minus 1. If you look at, try to make a three-dimensional drawing. So this is x, y, and z. Right? And now let's say you're going from, say, from the bottom to the top, right? You're walking like this. It's an important point. You need to understand radial coordinates. If I were doing this on the z-axis, so in Cartesian coordinates, I'm going from z equals minus 1, say, to z equals 0, and then to z equals 1. Right? That's what I'm doing. So I go from minus 1 to 0 to plus 1. But in spherical coordinates, this point down here is r equals 1, but theta equals pi. Right? Because I'm looking down. Right? Then I get to the origin, where r equals 0 and theta is irrelevant, because I'm at the origin. And then I go on to the next point, where r equals 1 again, I'm positive, but theta equals 0. So the difference is in theta, not in r. It's a ball, it's a sphere, yeah. Spherical is a ball, yeah. Okay? That's why r is just smaller than a. It's obviously larger than 0, I don't have to point out. Okay? Clear?
The sink is in the center of the ball.
The what?
The sink.
Particle?
Yeah, no, this function will be 1
this is,
in
so,
the center of the ball.
1? This is valid for r smaller than a, obviously, I said that, right? Because for r larger than a, you have 0. So this is true for r smaller than a, inside the well. It's a spherical well. I think of a football, a real football, not an American football. Then the particle is inside the ball, it cannot come out. That's what we're talking about. So this function is valid, obviously, inside the ball. Okay, everybody? Okay? So, second boundary condition. It must be 0 at the border of the ball, of the well. So we get here is, write it all out, say sine ka over a equals 0. Then we can divide by this normalization constant and multiply by this a. and we're left with sine Ka equals 0. It's exactly the same as in one dimension. So we get that Ka equals n pi. So K is quantized as n pi over A. Nothing new there. And when we plug this K back into the definition of K, we found the energy. So we can get out the energy from there. We get h bar squared pi squared n squared over 2ma squared. Exactly the same as in the case of the one-dimensional well. Now what are the quantum numbers of E? So first of all we have this n. That's the quantum number that we got from the radial equation. In addition though there's a little 0 here. And the 0 means L equals 0. So different L's, we didn't solve it, but I told you could have with the spherical Bessel functions. These L's wouldn't be 0, and the energy will look different. It will look actually way more complicated. That's why we have to indicate here this is En0. These are the eigenfunctions for the special case that L equals 0. Okay, so we have our eigenfunction, our eigenenergies. We almost have the eigenfunctions. All we have to do is normalize, so let's do that. So we have to normalize our functions. So let's first of all write out the functions. So the psi, right? It's this r that we found times the y. Well, we say we're now for the case L equals 1. So it must be this r and 0 times y 0, 0. If L equals 0, m can only be 0 because it must be between plus and minus L. So what we find is that it's a times sine n pi over a times r divided by r times this y 0, 0, which is 1 over root 4 pi. You can look that up in a table as well. This is the function has to be normalized. I'll add the quantum numbers to psi as well. It's psi n 0, 0, 3 quantum numbers. N, L, M. Right? L is 0, so M is always a 0, and N is the radial quantum number. I'll normalize the function, so 1 has to be equal to the integral on psi. That's a 3-dimensional integral. Right? d3r means I'm integrating with 3 dimensions. So this could be dx, dy, dz, but that wouldn't help much because I'm working spherical coordinates. So in spherical coordinates, there's an r squared dr from 0 to infinity. I hope you know this stuff. 0 to pi over sine theta d theta, and 0 to 2 pi over d phi. Then I take this wave function squared. So there's an a squared sine squared n pi over a r over r squared. And then there's this 1 over root 4 pi. Now I'll write it as y11. You'll see in a second why there's no need to go crazy and write out all the YLMs. So notice that there's a part that depends on r, and a part that depends on the angles. So we can write this integral in 2 parts. Also note that the r squared from the Jacobian cancels with this r squared in the denominator. So there's an integral from 0 to infinity. Sorry, from 0 to a, right? Because the well is only until a. In general, it's to infinity, but the wave function outside a is 0. So this is to an integral from 0 to a. Sorry about that. There's an a squared outside, dr sine squared. It's getting simple now. And there's a second integral. I've got the squared on the spherical harmonic. I'm going to call this entire thing here, right? I'm going to call this entire integral over the angles integral d omega, which is a symbol. When I write integral d omega, what I mean is this lot. And now you know that these functions are normalized, so obviously this must be equal to 1.
You say the nm is equal to 0.
Sorry?
Ah, okay.
Yeah, I'm confused. You're right. Yeah, it's y00, 0. Sorry about that. Obviously it's y00, 0. Integral d omega over a circumharmonic squared is obviously 1 because they're normalized. And then from this integral, we get a over 2. So we find, since this entire thing must be equal to 1, we find that a equals root 2 over a. That's the easy part. So we plug it back into the wave function, the eigenfunctions. So we just get 1 over square root 2 pi a. And then there's a 1 over r and the sine. There we go. These are our eigenfunctions. What are the units of this eigenfunction?
1 over square root of length.
1 over square root? No, it's not 1 over square root length.
Ah, yeah.
Notice there's a square root of a here, and there's an r here. So it's 1 over 3.5 length, right, in dimensions of psi. It's 1 over meter to 3/2. Why does that make sense? Because it's two-dimensional. So this thing squared is 1 over volume, and then the integral over a volume element will give you a number. So always check your unit when you're done. Make sure it's correct. In this case, we're fine. It is correct. All right. Questions about this? Okay. So we have solved our first spherical problem. We found eigenenergies, eigenfunctions. For the case L equals 0, I admit. But the only thing that is more complicated for L different than 0 is a technical difficulty, a mathematical difficulty of actually knowing special functions like spherical Bessel functions. If you know these functions and you're not afraid of them, which you shouldn't be, by the way, then it's exactly as simple. Okay, so we're ready to move on to the hydrogen atom. Yay! The highlight of the course. We started off by talking about the hydrogen in the Bohr model. We're now going to talk about the hydrogen atom in real quantum mechanics. And in your homework, you're going to compare the two systems and the two quantization schemes. And you're going to see the differences. That'll be a nice question for you to think about. But for now, let's learn about the real quantum mechanical hydrogen atom. So what is hydrogen? Probably shouldn't draw this circle anymore. That was Bohr, right? What is hydrogen? It is a nucleus, which is a proton. The charge here is plus E. The charge of the electron is minus E. And this electron is inside the potential that this proton generates. So it looks like a two-particle problem, but any two-particle problem can be reduced to a one-particle problem. And I refer to one of your very first homework assignments where you had a Hamiltonian for two particles and you showed that it could be separated. So this is exactly what is done here. You separate the two particles into one problem, and the only relevant coordinate is the distance between the two particles. Distance between the two particles, which is little r. So if I choose the origin to be inside the proton, then this becomes a centrosymmetric, or a central potential. So everything that I did beforehand applies. Angular momentum is conserved. I can write down easy Hamiltonian. And the only thing I have to know is what is the potential that this proton generates. And we know this simply from classical electrodynamics. It's this couple of constants, 1 over r, that's the main point, of minus 1 over r, the attractive potential, because one's negative, one's positive. And we're just going to call this k. It's 1 over r. Why isn't e squared here? I don't want that. Let's keep it e squared. E squared over r. So I'm putting all of these weird constants into some k, just not to write it every single time. That's just a convention. Okay, so the Hamiltonian in this case is exactly as above. It's this special.
The potential should be just E, I think, because the force is E squared. Right?
No, the force is r squared below.
Ah, E squared is in both.
I mean, what you're talking about is the electric potential, this potential energy. The electric potential has only E upstairs.
Ah, okay.
But the electric potential is not potential energy. Potential energy is the charge times the electric potential. It's confusing because we have called potential. But this potential energy. In quantum mechanics, from the Hamiltonian, we're always interested in energy.
Okay, so it's like the Coulomb force, but with the R.
Yeah, it's the integral of the Coulomb force.
Okay. Oh, okay.
Right, because the gradient of the potential energy,
minus, okay.
right?
Ah, okay.
But the gradient of the electric potential is the electric field, and the gradient of the potential energy is the force.
Okay.
It's a little confusing, but
Okay, I know it.
okay. So the Hamiltonian, right, is exactly what we had earlier. It's the radial part, the radial momentum. There's the angular momentum part. Actually, I shouldn't write like this yet. Started with operators. So this is L squared. I'll get to the actual presentation in position space in a minute. But in general, in any space you like, there's an L squared, and then there's the potential. So that's the easy part. Obviously, as I already stated earlier today, this commutes with both L squared and Lz. The middle term is trivial. Also, the other terms are quite trivial because they depend on r only, while angular momentum depends only on the angles. So obviously, they all commute. And also H with Lz, which is why there's a common basis to all three. It's also a 3D problem, so we expect 3 quantum numbers. So before we go into any special space and start going crazy with derivatives and so on, let's just say, okay, so there are 3 quantum numbers, so the eigenstates must be some ket with 3 quantum numbers, n, l, m. That's obvious before solving anything. We don't need to know the representation in any space, not r, not p, not anything. This is obvious because it's a 3D problem and because we have 3 operators. And the only thing we then have to know is how these operators act on this ket, on these eigenstates. And we know that as well. We know that the Hamiltonian operator takes out the energy. We know that the L squared takes out the LL plus 1. And we know that Lz takes out the m. We know that already. So you really see that although we haven't actually found the position space representation, we can already say an awful lot about this problem without actually doing anything. So the H operator takes out the energy. The L squared operator takes out H bar squared LL plus 1. And the LZ operator takes out H bar times M. Now something which is not as trivial, but can be found, and you do this in the lecture, is that this En is equal to minus k squared E squared over 2AB over N squared. AB is the Bohr radius. Why does the Bohr radius appear here? Well, I didn't have to call this the Bohr radius. Remember, the Bohr radius is just grouping together a couple of H bars and a couple of E's and some other constants. So these constants all appear here, and then I recognized, oh, I know that constant. I know that group of constants. I've seen it in the beginning of the course. So let's just call it here the Bohr radius is, again, I remind you the Bohr radius is the Bohr model, the radius of the atom in the ground state. And that obviously is some sort of length scale that is relevant to the hydrogen atom. You'll explore in your homework what the actual meaning of the Bohr radius is in the real quantum mechanical picture. But it's obviously a relevant length scale for the problem. So it makes sense that the Bohr radius would appear here. So if we know this stuff, right, this is like our dictionary or our resources. With this we can solve a lot of problems without even getting into position space. A couple of important conditions to know on the quantum numbers. So n must always be larger, not larger or equal, but larger than L. L must be greater than 0 or equal to 0, and as you know, m must be between plus and minus L. These are the conditions on the quantum numbers that you should remember off by heart. Obviously, all the states are orthogonal. And they're orthogonal in every single quantum number. So only if n equals n prime, L equals L prime, and m equals m prime, you get something which is non-zero. If two of the quantum numbers are the same and one is different, then the inner product is 0. That's why there are 3 deltas here. And obviously, this is a complete set, so any 3-dimensional function can be expanded as a superposition of these states, where we have to sum for n from 1 to infinity. It has to be greater than L, and L starts from 0. So n has to go from 1 to infinity. Then we sum for L from 0 till n minus 1. And then we sum from m from minus L to plus L. So the border of the sums are obvious from the conditions. And this is just a statement that this is a complete basis. Nothing new about that. We've seen it many times before. What is the ground state of the hydrogen atom? What are the 3 quantum numbers of the ground state? Obviously 1, 0, 0. Ground state are the smallest numbers that you can give to n, L, and m. So look at the conditions. Obviously the smallest numbers are 1, 0, and 0. N equals 1. And both L and M equal to 0. So the ground state is 1, 0, 0. What is the first excited state? So So you must have n equals 2, right? But if n equals 2, then what is L?
0.
Could be 0, in which case m is also 0, but there are also more options.
-1.
Right? Because if n equals 2, then L could also be 1. So there's also 2, 1, 1, and then there's 2, 1, 0, and there's 2, 1, minus 1. So you see that the first excited state is fourfold degenerate. Some people also use different notations for these states. They call this one S, where 1 refers to the quantum number n, and the S means that L equals 0. In analogy, this state here is called 2S, n equals 2, and here also again L equals 1. And this group is then called 2P, where the P means that L equals 1. It makes sense to group these together, because as we saw last week, that if the L is the same, but the M's are different, this forms a subspace, and you have your operators L plus, L minus, that can take you within this subspace. So it's a closed subspace, which might make sense to have a common name for all these states. These notations are used in chemistry and atomic physics, so you should know them. As I mentioned, this state is fourfold degenerate. In general, the nth state has a degeneracy of n squared. So n equals 2 is 2 squared, so 4 times degenerate. N equals 3, therefore has 9 states, so on and so forth. It's a nice exercise to try and write down all of the states for some high n. Take like n equals 5 and make sure you can actually find all 25 states. That's a good exercise to, I'm sure I've given to you in the homework. Next time. It's a good way to make sure you understand these conditions. Okay, position space. That's where it gets fun. Knowing the wave function position space will let us calculate probabilities of where to find the electron. Will it be closer to the nucleus, further away? Will it be in the upper hemisphere or in the lower hemisphere? In order to calculate probabilities like this, we have to find the representation of the wave function in position space and then take the absolute value squared. Right? That's why this is important. So obviously, this is notation. So when I'm taking these NLM functions and I'm projecting them onto R space, I get a function psi NLM, which is a function of 3 coordinates, r, theta, and phi. And we have seen that this problem can be separated into YLMs and some radial function, because it's a central potential. We get that for free. You can find these R and L the same way we did for the previous example, finding U, imposing boundary conditions, and so on. It's a long exercise. You should have done it in class, and then you find some really weird and long function. I'll just write it down once, and to make sure you're not afraid of it. But you get this really long function. The exclamation mark is a factorial. next part, 2r over NAB squared. Sorry, to the power of L. And then there's capital L, 2L plus 1, N plus 1, 2R NAB, e to the minus R over NAB. So a couple things about this function. I'll give you a second to copy it down, but I'll say a couple of words. So this scary thing in the beginning is not scary at all, it's just normalization. That's all it is. Functions have to be normalized. So this is normalization. Don't be scared of it. It has N and L in it because something in the end here is not normalized properly. So we have this scary looking thing in the beginning. It's just normalization. And you see the units as well. AB is in length. It's to the power of 3 and then a square root. So this R will have the correct units in the end. Excuse me?
What's L?
What is L?
No.
This L, we'll get in there. This term beforehand. Everything here is dimensionless. So the next term here, for instance, you see there's an R, which is a length, divided by AB. So it's dimensionless. And as I said, AB is a good scale for the length scale for the problem, which is why it appears every time as an R. R over AB, R over AB, R over AB. But this Bohr radius appears everywhere as an R. That's why it's a good length scale. This is just some power, R to, it goes like R to the L. And this thing here is what we call a logger polynomial. So it's just some polynomial, like the Hermites. You can look them up on the list. So it's a polynomial, so it's R to the power of something, and it's multiplied by R to the power of something else. So this total thing here, the R to the power of L times the logger, is another polynomial. So it's nothing to be scared of. Right? It's just R squared, or R to the third, or R to the whatever. So nothing to be scared of here. And then in the very end, there's a decaying exponential. And this is the most intuitive part of the function. It's decaying, so when R goes to infinity, this entire thing will be 0 due to the exponential.
What's that under polynomial brackets?
This is the argument of the polynomial.
No, I can't read it.
2R over n times the Bohr radius.
Oh, okay.
Sorry for my... That's why I type my notes. It's readable. Okay, so this is the most intuitive part. Obviously, as R goes to infinity, the wave function must go to 0, and this will take care of it. So simple, right? It's long, it's messy, but if you break it down into parts, there's really nothing to it. You do not even have to be scared of the fact that this Lagrange polynomial has 2 quantum numbers. It's like the violins. Those have 2 quantum numbers. Just that here the quantum numbers are not just n, but n plus 1. But we could have, in the same way, chosen the quantum numbers to be here just, really find a new quantum number, which is n plus 1. And then define another new quantum number, which is 2l plus 1. And then these Lagrange polynomials would look simpler, but then the energies and violins will look complicated. So it has to be complicated somewhere. Let's just stick it into here. But obviously it's just a convention and there's nothing to it. So I hope you're not scared. If you are, then, well, that's your problem. Questions? Okay, so let's go on. Let's look at the orthogonality in position space. So what happens to orthogonality in position space? So if I want to take the inner product between 2 different wave functions, I have to integrate over entire space. So there's an r squared dr, and there's an integral d omega. So it's the angular part, sine theta d phi. Then this NLM needs a complex conjugate. So there's this r and l of r. It's a real function, as you can see. So there's no complex conjugate to take. But the YLM that follows is a complex number or a complex function. So here I take the complex conjugate. And then there's this ket, which is just the wave function with no complex conjugate. And I have primed all of the quantum numbers in the second wave function. Now obviously this is separatable. That's how we designed the question. So there's an r n l r n prime l prime. That's the first part. And then this thing is multiplied by the radial integration what I'm saying here is trivial, but I want to point it out. You know the YLMs are orthogonal, so this is delta LL prime times delta MN prime. But these radial functions are also orthogonal. They might not look like it, but they are orthogonal. Obviously, you have to use this r squared for that to be true. There's a weight function. But this is delta n prime, delta LL prime. So in total, obviously, the entire thing is orthogonal. But note, my main point of what I'm trying to say here is that both the YLMs are orthogonal by themselves. The radial functions are orthogonal by themselves. Not only the total wave function, but each part individually is also orthogonal. This is very useful when you calculate stuff. All right, example.
Should we then have the delta squared?
What is delta squared though? You mean this delta times this delta? It's 0 or 1, right? So it's either 0 times 0, which is 0, 0 times 1, which is 0, but obviously it's not because it's the same delta, or 1 times 1, which is 1. So it's just 1 delta. We're given two wave functions at t equals 0. First one the superposition of 1, 0, 0 minus 2, 1, 1. These are hydrogen eigenstates, obviously. And the second wave function we'll consider is 1 over root 2, 1, 0, 0 minus 2, 0, 0. So we're considering two different hydrogen atoms. One of them is prepared in this state. The other is prepared in this state. And we would like to find the distance, the probability to find the electron at a distance r from the nucleus. Electron at distance r from nucleus. We'll call that P of r. So as I said, the atom is the nucleus, right, the proton, and then there's this electron which is somewhere surrounding it. So when I'm asking about the distance, because it's a spherical problem, I'm asking what is the probability to find the atom, the electron, inside a spherical shell of width dr. Right, this is the distance r. So what is the probability of finding the electron at the distance r from the nucleus? That's this distance r, so it could be anywhere on the sphere. And because it's 2 dimensions, right, it's always a dr, so there's a width dr, and then there's the distance r. So that's what I'm asking. What is the probability to find the electron in this region? Okay? let's solve the question. Let's do one after the other. We would like to do this for each wave function individually. And then we'll compare the two. Maybe we'll learn something interesting, like comparing two different initial states. And let's say we know all of the radial functions. They're given to us. I'll write them down when they become relevant. So what we have to do, let's say we know the wave function, right? So we find the wave function at some later time t. I don't say that. At t larger than 0. So let's say we find the wave function at some later time t. Take the absolute value squared, right? Multiply by some volume element, r squared sine theta dr d theta d phi. And what is this? This is the probability of finding an atom at a point in space, r theta phi, that it describes a point in space. This will not give us the probability to find it inside the shell. It will give us the probability to find it at some point, right? Because here there's an angle theta and angle phi. This is not what we're looking for. So what we have to do is integrate over all the angles. So P of r is what you get when you actually take the integral. So I'm taking the integral d phi. Taking the integral over theta and phi over the entire space. So over the entire 4 pi steradian. But no integral over r, because I'm interested in the distance r. I don't want to kill that. So this is what I actually have to do. This point clear? This is one of the main points I'm trying to teach today. It's a three-dimensional problem, but the question is one-dimensional. So I need to integrate over the remaining dimensions. Okay, so let's start with psi 1. So let's find psi 1 at a later time t. That is really simple. We're already working in the energy eigenbases. So all we have to do is add the time dependence of each eigenfunction. So there's E1 for state 1, for state 1, 0, 0, to the ground state, minus e to the minus I E2 over h bar t 2, 1, 1. Now I'll take the absolute value squared of this thing. Let's first of all write it out in position space. So it's 1 over root 2 e to the minus I E1 over h bar t. Then it's an R10 times a Y00. And the same thing for the second function. The radial function carries the quantum numbers 2 and 1, and it's the spherical harmonic Y11, which is going into projecting onto position space. Okay, now let's take the absolute value squared. So according to this formula, call this P1 because it's the probability of finding the wave function number 1 of R and T. So plugging into that formula, we have integral d omega, right? This is just d omega, this thing here. There's an r squared dr, integral d omega. And now this thing squared will give 4 terms. So the first term is r10 y00 squared. Second term is this thing squared, so that's r21 y11 squared. And then there are 2 more terms here a minus sign, which is this times this, and then the composite conjugate, right? So there was a R10, R21, Y00, and then the composite conjugate of this one is Y11 times e to the minus I E1 minus E2 over H bar T. And then there's another one like this, which is the common conjugate of this one. So after you do quantum mechanics for a couple of years, it becomes simple to write down these functions. And these expressions. Now notice what happens. What I'm going to do next, I'm going to spare you of writing it out again. So what I'm going to do next is take this d omega, right, and move it in front of the four terms, right? So I can move this in front of here because the r doesn't depend on the angles. So the integral over y00 squared, that's just 1 because they're normalized. And here I get the same thing. And when I move the integral here over y00 times y11 star, it's obviously 0 because they're orthogonal. And the same thing happens here as well. Okay, is that clear? Moving and doing each integral independently, and I'm just doing the integral of d omega. And because the YLMs are orthogonal, these two terms just cancel. So what we then get is that P1 of R and T is time independent. Notice that all the time independence is cancelled. So it's R squared dr. I'm missing a 1/2 from the root 2 squared. Is R squared dr over 2. And then there are these two terms, R10 squared plus R21 squared. These are functions of R. You can go to some table, some internet website, and find these functions, plug them in. They're just polynomials times an exponential. So you found the probability to find the particle inside such a spherical shell. Notice time independent. Did you expect that? So think about it, what is supposed to be expected. In the meantime, let's solve the same question for psi 2. So psi 2, this function, we're also going to write it out in position space and add the time dependence. So it's 1 over root 2. Then there's the time dependence for 1, 0, 0, which is e to the minus I e1 over h bar t. And then the radial function is 1, 0, and then there's a y0, 0. And then the second part is e to the minus I e2 over h bar t, r2, 0, and then y0, 0. Okay, that's the easy part. Notice that now this y0, 0 appears in both terms, so it can be factored out. Right? So this will take a very simple form. So it's 1 over root 2 y0, 0. And then there's an e to the minus I e1 h bar t r10 minus e to the minus I e2 over h bar t r20. Okay, and the y00 is now outside. Now when I want to calculate the probability, call it P2, I have to, according to the formula, integrate over d omega, and then this thing squared. So there's a 1/2, and then there's a y00 squared, and then there's this thing times its complex conjugate. So there's an r10 squared plus r20 squared plus r10 r20 times, there's a minus here, times e to the minus I, let's call it omega 1 2 t, plus e to the I omega 1 2 t, where I've defined omega 1 2 is e1 minus e2 divided by h bar. Okay, so just multiply this by its complex conjugate. Now, this entire bracket that appears here depends on the radial coordinate, depends on r, but not on the angles. So the integral d omega is only on this part. And since it's a spherical harmonic square, it's obviously just equal to 1. So now, you see that your probability is not time independent. It's these radial functions, which once again you can look up in the table. But then there's this cross term, which is a cosine. So now you see that you get this interference term, which is time dependent, which you did not get in the first case. So this is time dependent. Why did this happen? Why did we once get a solution that's independent on time and once a solution that is dependent on time? Remember, both our initial functions were superpositions of two atomic states. So what was so different between these two that looked so similar that one is time independent, one is time dependent?
Angular momentum.
Very good, angular momentum. Our initial states, we still have them. So one of them had quantum numbers, here's the first one, right? It had 1, 0, 0 and 2, 1, 1. So here L equals 0 and here L equals 1, right? The other wave function is kind of still here, right? This is 1, 0, 0 and this one here was 2, 0, 0. So both of them had L equals 0. Now the fact we had to, right, our question was angle independent. We didn't care about where the atom is angle-wise, we only care about the distance. And angular momentum will only affect the angle. So it's called angular momentum. So if the angular momentum is orthogonal, then it cancels out. But if it is the same, then it can interfere. And we get interference term. All right, so we've learned some physics. Cool. Okay, we have another 10 minutes. In this 10 minutes, let's discuss the Zeeman effect. So we're now going to take our hydrogen atom and we're going to pull it inside a magnetic field. Sound scary? It's not. It's actually very simple. Let me show you what I mean. Zeeman is just the name of the guy who, I don't know, invented it or noticed it, or I don't know what he did exactly, but it's just the name of a person. So the Zeeman Effect. So we take a hydrogen atom in magnetic field B. It's a vector. The Hamiltonian of the entire system has two parts. HA is the atomic Hamiltonian, that's why it's called A, and HB is the interaction of the atom and the B field, magnetic field. That's why it's called HB, such as AB is an ABC, it's A for atom and B for B field. So we know the atomic Hamiltonian. That's what we've been talking about the entire lesson. That's our atomic Hamiltonian. And the interaction looks as follows. It's mu, which is the magnetic moment of the atom, times the B field, magnetic field. Now the magnetic moment is an operator because it's an observable. I can measure the magnetic moment. It's like a magnet, right? So I can measure it, which is why it's an observable, and we know that with every observable we can associate an operator. So the magnetic moment is an operator. How does it look like? It's actually just a couple of constants. Remember correctly? Don't worry about what they are exactly, it's just all positive constants. Mu B is called the Bohr magneton, G is the gyroscopic ratio, and H bar is the Planck constant. So it's a couple of constants times the angular momentum operator. Now this makes intuitive sense. Let me try to explain why the magnetic moment is the same as angular momentum. So in order to understand this, we could just consider the classical picture. Why is there angular momentum in an atom? Because in the classical picture, the electron is circling the nucleus. If something is doing a circular motion, it carries angular momentum, right? But in addition, the electron has charge. So now we have a charge going in circles. There's a current. What happens when the current moves, or when there's a current? Generates a magnetic field. So the atom, which is basically an electron going in circles, generates a magnetic field in the up direction, or down direction, whatever direction of the electron is. Right? And magnetic field pointing up is exactly the same like a magnetic dipole. It's the same field you would get from a magnetic dipole. So the dipole moment is the same as the angular momentum. The negative sign has to do with the fact that if the electron's going in one direction, then the current is by definition going in the opposite direction, because it's minus E. Right? That's why there's a minus sign here, and then the minus sign goes away again in this interaction Hamiltonian, which carries another minus sign. So you can understand this intuitively. So it looks like a big problem, like a messy problem, but you'll see it's actually very simple to solve. We'll actually do it in 5 minutes. The only thing we want to find are the eigenstates and eigen energies of this atom in the magnetic field. So let's make a wild guess. The eigenstates of the first part of the Hamiltonian, the atomic part, we know what they are. They're the NLM states. Now, these NLM states are the common eigenstates of three operators. The Hamiltonian of the atom, L squared, and Lz. I'll tell you one thing. For B equals B0 Z hat. So it's a uniform magnetic field in the Z direction. forgot to tell you that, sorry. So we know, as I just mentioned, that NLM are eigenstates of three operators, the atomic Hamiltonian, L squared, and Lz. Now let's look at the second part of the Hamiltonian. Let's plug in what we know. So it's minus the mu, which is a bunch of constants, a bunch of numbers, times the angular momentum operator. And then this is multiplied by B naught Z hat. So a vector times a univector is like the projection of this onto Z hat. So this is just, once again, a bunch of constants, or the minus one away. So it's a bunch of constants, mu B G B0 divided by H bar. Then the only thing that's left is the Z component of the angular momentum. Now, look how great that is. This Hamiltonian is up to some constants Lz. And these are eigenstates of Lz. So the eigenstates of the total Hamiltonian are just these NLM states. That was easy. All we have to do is find the explicit expression for the Hamiltonian. And now we can find the spectrum. So we can find the Eigen Energies by simply applying the Hamiltonian on these eigenstates. And whatever comes out, these are the energies. So the first part will take out the energy of the atom, right? We had that earlier on the board. It's minus k squared E squared over 2ab 1 over n squared. That's just a spectrum of the hydrogen atom. And then the second part is acting with this on NLM. So it's a couple of bunch of constants times whatever this does. This takes out h bar m, so h bar cancels. So there's plus mu bg b naught, bunch of constants, times this m, which is the quantum number, not the mass, it's the quantum number m, and of course this thing times NLM. So these are the Eigen Energies. Notice that now they depend on n, as they did before. In addition, they also depend on this m quantum number. So just before we end, let's make a plot of the energies versus the magnetic field. And what happens if I put the atom somewhere in space and then slowly turn up the magnetic field? What happens to the energy levels? So the ground state starts off here at minus 13.6 electron volts, right? That's the ground state energy. Plug in the numbers here, you'll get minus 30.6 electron volt. So the ground state is 100, right? So m equals 0. So it won't be affected by the B field. Let's see what happens at for n equals 2. So you get about minus 4 or something like that. Minus 3 point something. Right? For the n equals 2 states. So there are 4 states there, right? There's states that live here are 200, 211, 210, and 21 minus 1. And we saw earlier that they're all degenerate. But the magnetic field, inside the magnetic field, the energy changes. So these 2 states, 2, 0, 0, and 2, 1, 0 are not affected by the magnetic field because m equals 0. So this term drops off. So they're constant as a function of the magnetic field. This is 2, 0, 0, and 2, 1, 0. But now, the state 2, 1, 1 will increase as I increase the magnetic field. And this one, 2, 1, minus 1, so m equals minus 1, there's a minus sign here, so it will decrease with magnetic field. So you see what the magnetic field has done is it has lifted the degeneracy in the quantum number m. It is still degenerate in L. These two states are different in L, they're orthogonal, but have the same energy. But the m, the degeneracy in m has been lifted. And for this reason, this m quantum number is also called the magnetic quantum number. Because you can lift the degeneracy, you actually see this magnetic field, or this effect, inside a magnetic field. So it's called the magnetic quantum number. Cool effect. Question about this? All right, so we're done for today. You have nice homework, and we'll meet next week one last time.